Everyone, thank you for coming back on time. This is excellent. It's now time to hand over back again to Robert Collins to teach us about, is this the OpenStack on OpenStack talk? Indeed it is. Please welcome him.
Testing. Right. If you can't hear me, there's something wrong with you this time, not me. Right, so I did this slide before. If you've come into the room since I did it, tough. And I seem to have deleted one of my slides, which is going to make this a very interesting talk. You wanted a white background for testing with the recording, so I think we've achieved that. So, this sounds awfully loud to me. Is that better? I can just hear it echoing back from somewhere. Oh yeah, Django. Well, yeah, let's all go there. Okay, no, seriously. So the OpenStack and OpenStack project, we're about to, at the moment I'm actually writing a mission statement for the upstream engagement of this to turn it into a program. Until now we've just been an effort HP's been funding, and some other organisations have joined in as we've gathered some momentum and some capability. What we're trying to do is to make OpenStack easy to deploy, because OpenStack, as you know, part of this whole cloud focus on automating all of the things on that cloud thing. I'm sorry, it's going to be the standing joke for the day. And since I'm giving about 4 talks, you're going to get very bored of it. If you can't deploy OpenStack, you can't get any of the benefits of it unless you go to someone else, to a cloud provider. And while there's lots of cloud providers around now, and there are going to be more in future, it's actually quite useful to be able to do it yourself. Many people already have hardware inside the data centers that they're using for testing or for their production deployment. They want to be able to repurpose it, reuse it, consolidate it, and would like to make that really, really easy to do. The big thing for me, I have a long history in testing. Software testing has been a bit of a passion of mine for a long time. And if you don't have the ability to set up a clean, dedicated test environment and do that in a repeatable way really, really quickly, it becomes very, very hard to get good, serious confidence in your software. So one of the things we want to be able to do when we talk about a deployment is you want to be confident the deployment's going to work. So you want to be able to develop and test the cloud layer itself as well as the software that runs on it. And this is the actual plumbing involved in OpenStack. This is a simplified version of the plumbing involved in OpenStack. The slide that was deleted is a very pretty slide that says you have compute, you have network, you have a UI, you have storage. You know, it's like the big block diagrams that Tim was showing before. This is the actual dirty secret. And as I say, this is a simplified version because it doesn't show the fact that nearly any one of these individual components, have I got my, oh, no. It's going to be one of those days, isn't it? One of these buttons. I'm going to give up on that. Yes, so if you look at one of these buttons here, quantum plugins here, that actually says there's about 20 different things you could have substituted in for that box. So your ability to predict whether it's configured correctly and is going to work well is hugely dependent on exactly what components you've picked from the whole ecosystem to be your quantum plugin or to be your Nova driver plugin. Tristan, can I relate the issue you had with that? Yeah, so when Tristan tried to run up 3 VMs before and that failed, that was because he's got a different plugin for his virtualization layer. He's talking to VMsphere, and VMsphere has a limit on how long an instance name can be. When you boot multiple instances in OpenStack, to differentiate them, they don't all end up with the same host name, they get a UID appended to the host name. And this combination was longer than the length that vSphere allows. So that driver has a bug. Big deal. But your ability to predict whether you're going to have that bug or not is dependent on the fact that this is an abstraction layer. So when you actually go to deploy this huge fragile thing whose behavior you can't predict, it can break. It can break when you install it can break when you reconfigure it, and it can break when you upgrade it. It can break due to bugs, like the one we just had. It can also break due to entropy. If you have an environment where someone has logged in and done some debugging on a node, and they've installed a debug package, they've updated the kernel, they've tweaked the driver configuration, and you've got 400 nodes with one of them that has this slightly different behavior, it's a pretty sure bet at some point that node's going to break, and everything running on that node is going to fall over and disappear, and your client tenants are going to be going, hey, I thought this was reliable infrastructure, or at least reasonably reliable. I mean, so one of the things that's not always talked about in the cloud, when you look at the different layers of the cloud, an application as a service, you expect to be always available everywhere as long as the internet is working. Great. A platform as a service, you don't have that expectation. You expect that the platform as a whole will be available, but any individual instance of software running within it might get crashed, might get terminated, might get swapped out. It's got no reliability at all. So what you do is you run 5 or 10 Django instances in parallel in that platform, and as a whole, you're now highly available. You have your databases clustered, you have everything with redundancy, but the individual components are allowed to fail gracefully. And when you go down to the infrastructure as a service layer, which is the one that platform as a service layers are generally implemented on top of, you also have that expectation that virtual machines are not reliable. They're not the same as physical machines. They don't have innate redundancy. So they might get migrated, they might suffer computation pauses for a couple of seconds while they get live migrated somewhere, and you're meant to architect your applications and the things you build on it to deal with that. So while in theory everyone has this expectation and everyone understands this trade-off, the reality is no one does. And everyone gets extremely unhappy when their VM suddenly stops working because the compute host it was on has suffered a kernel fault because there was a third-party driver there that nobody knew about that was put there a year and a half ago. And this is the sort of thing I've seen happen. I'm not making up random stories. This is how things break. And lastly, of course, you can actually have hardware fail. It's kind of hard to live migrate a physical machine somewhere else. You need to buy one, walk it in, plug it in, and then worry about getting the data across. So what we're trying to do with OO is to bring continuous integration, so testing the configuration, testing the software, testing the whole running production quality stack, testing the delivery of it, how you get it onto the metal, making sure it's predictable, reliable, robust, make it easy to install, make it easier to maintain. You're still going to need knowledge about what you're doing, but it shouldn't be a learning curve like it is today. We want to encapsulate the installation upgrade process so that we can test it, so that we can gain confidence it's going to work, and we want to be able to test the actual impact of a migration, of an upgrade in real time. And one of the things that we're using to do that is the same APIs. So the existing deployment technologies you can download, things like Crowbar or Juju, use different plumbing to deploy OpenStack than you use to deploy virtual machines in OpenStack. And this means that if you're writing a script, for example, that deploys OpenStack in your production environment, you now have to have a different script, or at the very least a different plugin for your deployment engine to test it inside a virtual machine environment. And that means you can no longer gain any confidence, or it's reduced the confidence you can gain, a less extreme position, by virtual testing of your deployment capabilities. So we have a strategic focus that everything that OpenStack offers, we will use that offering so that you have the same API, whether you're testing, doing a test deployment to bare metal or a production deployment, the same API at every step along the way. Reduce the number of variables that you have to consider when analysing whether something is a good indicator and is ready to go live. To tackle these different sorts of failure modes, we've got different strategies. For bugs, we think CI/CD is a good strategy for uncovering bugs. We're going to find out what's going to go wrong if we have reasonable test coverage. It won't help us deal with cruft at all, and it won't help us deal with hardware failure. Doesn't give any sort of indicator for that. Who here is not familiar with the concept of a golden image? Right, okay. So the idea of a golden image is that you, actually I describe it in about 3 slides. So the core concept though is that we build something that has reduced opportunity for entropy, and then we use that to do the deployments. And obviously we need a highly available setup of all of OpenStack, and that means all of OpenStack needs to be able to be deployed in an HA fashion, which is kind of true today. So the overall OO deployment story for an organization that was to deploy OpenStack using OO is that you would start with a developer uploading a change. Now, we're focused on trunk OpenStack because releases are just a great way to keep bugs, right? When the software is released, all the existing bugs stay there. Of course, you avoid the risk that new bugs will be added, which is why a lot of organizations that are risk averse want to consume releases. But from our perspective, we know just how many ways there are that a cloud environment can decay, like hardware changes out from under you, drivers change, the virtualization engines people are using are changed, the standards people are writing to change. We think it's a much better trade-off to take the possibility of new bugs and the absolute confidence that existing bugs have been fixed than the other way around, at least today. Maybe in 2 years' time, there'll be a different story. But you start with a change coming in. That might be coming into upstream OpenStack, and we're aiming to have this be part of the gating process for OpenStack itself. But also within your own organization, if you were picking a fix from upstream OpenStack and bringing it in, you'd run through this process locally as well. So there's no change. You take that and you build a disk image, a machine image that you can boot that has the OpenStack code with that change incorporated in it on the image. You then deploy that and test it. On a small scale, just that thing in isolation. You put the result to the side. If it fails, there's obviously a problem. Tell the user you failed your test run, you can't land this commit. If it works, we go to a more sophisticated test where we build a whole cloud from scratch. We deploy a bare metal cloud that can deploy physical nodes, and we give that bare metal cloud the compute image or the control plane image or whatever image was affected by this code change, and we ask it to scale that up onto a machine. We give it a workload. We migrate it from the previous version of these images to the new version, so we can see that migrations work. There's a certain amount of science fiction here, but it's all coming together. This is an in-process thing. We use Heat, which is the orchestration tool within OpenStack to coordinate all of this workflow, so we don't have lots of little custom bits of code right into the Nova API. We just have one description in Heat, and we say, hey, here's your initial description, here's a new description, go. At the end of the process, if it all worked, we say, yep, we've got great confidence that's ready for production use, and we then go to the production copy of Heat, and we say, please deploy this cloud, using the same images. So we're not recompiling or rebuilding anything. If those images worked in test, it's pretty easy to say the same images should work in production. Now, I haven't really talked about things like Chef or Puppet or anything so far, and they're actually not part of our story at all. And here's why. When you look at the problems that we need to solve in deploying a multi-node, multi-tier application on bare metal, we need to solve machine provisioning. We've got to be able to take a whole bunch of machines and convert them into parts of that cluster. We've got to get software on those machines, so more than just having the machine configured correctly at the sort of RAID controller level, we have to have the right OS on it, we have to have the right configuration within that, and we have to manage state. There's local state that gets stored in these machines. The database files, things like Swift that store persistent storage on the machine, that needs to be taken care of. And finally, we need to glue them all together. We need to take the fact that one machine is a compute node and other machines need to be aware of that so that they put it into the right Nagios monitoring group. Load balancers need to know where they back-end traffic to, that sort of thing. Who here is in an ops or sysadmin or a DevOps kind of role? All right, so I'll spend a little bit more time on this. So from our perspective, things like Chef and Puppet really don't help with service orchestration or hardware provisioning. You can build stuff on top of them to do both of those things, but that doesn't mean they're actively helping you. They're kind of there, but they're not directly supporting it. They weren't designed for it.
Have you guys compared Salt to Chef and Puppet?
Have we compared Salt to Chef and Puppet? Yes. And I believe it fits exactly in the same category. It's got a somewhat better design in a number of ways, but it's not actually trying to solve these other problems. Now, I'm not saying it should solve the other problems. That's the next point I'm going to get to. Things like Juju and Maz tried to solve too many problems. They try and solve everything all at once. And just personal engineering preference, I prefer a small tool that does one thing well, which I can easily understand. If there's something going wrong with it, I have a small manual I need to read, a small amount of code I need to look through. And I'd like a bunch of those tools that cooperate well together. So O is built then on using Nova to do machine provisioning, both physical machines and VMs. We use a thing called Disk Image Builder to do the software installation. Now, Disk Image Builder is a very thin wrapper around chroot and make ext4 file system and copy the two things together. We don't actually run an operating system installer ever. What we do is take a vendor-provided image like the Ubuntu Cloud Images, or recently Red Hat have got Cloud Images available, and we suck that down in through Disk Image Builder and then we customize it. The customization to add an Ethernet card that Tristan did just in time as he did the deploy, that's the sort of thing you can do in Disk Image Builder to transform your input image to one that's suitable for your environment. And the reason you might want to do that as a part of building a new image rather than doing it just in time is because you want to be sure that it's there, that there's no opportunity for it to go wrong. If the metadata server isn't available, you still want to be able to get to the instance on your management network. It removes the opportunity for a number of failures to occur. It also means you're not shipping multiple kilobytes of arbitrary code out to an instance and hoping that it does the right thing. All the code is there on the instance in advance. For configuration, the last mile tuning of the instance, we don't do any software installation. So this is a principled thing. Software installation is part of software image building. Configuration is telling the software that's already installed what to do. And this is also a performance thing. If you're doing lots of deployments, you can spend a very, very large amount of time and depackage your RPM very, very easily. We do it once, and then we forget about it. Never have to do it again until we've actually got a new version, and then we push out a new image. Things like rsync for live machine updates are very, very efficient at just copying the changed files. For state management, so Disk Image Builder, Apply config and Refresh config are just small tools that know how to build a disk image, take a configuration metadata description in JSON and write it down to etc files on disk, and run migration scripts. So the Refresh config knows how to run a sysadmin script that's involved in updating, for example, the schema of a database or something. So that's the place that you hook in your Nova DB sync commands or whatever else. And Heat is service orchestration. So when we started this project, there was no bare metal driver in Nova. So if you wanted to do physical machines, you had no options. But there was a patch set that NTT Docomo and ISI had been working on that added such a driver. And we were like, yes, this is great, we'll use this. A year later, and it's been completely rewritten and it's nearly usable. More seriously though, it's the initial patch set worked, but there was a lot of friction in the design between the way Nova thought about things and the way this patch set wanted to think about things. In particular, if you think about the problem of a VM creation system, you've got a big compute node, it might have, let's call it 100 gig of RAM, it might have 50 CPUs in it. I know these numbers aren't exact ones because of the way the architecture works, but it's easier to talk about round numbers. 100 gig of RAM, 50 CPUs, and you can subdivide this. You can subdivide it down to fractions of a CPU because you've got your host hypervisor is able to time slice between VMs. And you can slice it down to very small amounts of that RAM, although you probably don't want to force VMs to actually be swapping when they're running, because that would be bad. If you've got a physical machine and you're going to put a physical workload onto it, you can't do that. It's not subdividable. So if you model a collection of physical machines as one big machine, maybe that will work. It turns out it doesn't, because you can't subdivide arbitrarily. Each individual machine has to come out as exactly its size. If you try and schedule a VM with one CPU and a gig of RAM into a cluster that's made up of 24 core machines with 100 gig of RAM each, the numbers aren't going to add up, and the Nova scheduler gets very, very, very confused. So there was a bunch of work that had to be done there. Anyway, the upshot is we now have this project called Ironic, which is probably going to be just usable in Havana and really, really good in Icehouse. And it's abstracted out that bare metal driver to a separate project because it turns out that we actually want to be able to talk to Cinder for block storage, and we want to be able to talk directly for Neutron to be able to do physical reconfiguration of your actual network infrastructure. Rather than an overlay network, we want to reconfigure actual fabric to say this machine is now part of that tenant and can't see anyone else's broadcast traffic, thanks. So rather than being buried as a small part of Nova, we actually need to set up at a more directly a visible layer. We've got the three projects I just mentioned and Heat. Now, the way Nova bare metal works is it's got pluggable backends itself, and this is another reason to move it out to a separate component, to Ironic, because Nova's pluggable with different virtual drivers. Having a virtual driver that itself is sub-pluggable didn't really, kind of hinted that there was something a bit wrong. But the default, the reference implementation is just PXE and IPMI. Now the sysadmins here are probably going, yeah, yawn, this is like 1996, it was working, why are we... But it's kind of useful to put an API on it. The same API that boots a Nova VM will boot a physical machine, because we take care of all of the plumbing to tie it together. The specific mechanism is that we PXE boot it, we use IPMI to tell it that we want to PXE boot, and we deliver a disk image, a RAM disk and kernel for the boot that will then talk back to our server and say, hey, I'm available, here's my iSCSI endpoint details. We then talk to it over iSCSI, we repartition it, we DD the disk image onto it, and then we reboot it again. Now, an implementation quirk today is that we don't actually reboot it off the local disk. We reboot it over the network again, and this time we give it the RAM disk and kernel for that the end user supplied. Now, arguably we should allow local boot blocks, but it's actually a lot easier to keep net booting working every time than to recover something that's got a bad boot block when the end user doesn't have physical console access to the machine. And you probably don't want to give them physical console access to the machine. So while we may change it to make it optional, this is actually the preferred way that we have for deploying OpenStack. With two exceptions, and those are the two machines needed to bootstrap everything back up again after you turn the whole data center off.
Just a point on that, Hobart is the same thing, of always net booting, because
Right.
then you can always reconfigure them or redeploy them. Or,
Tim is saying that Crowbar does the same thing for much the same reasons. Yep. Okay, so Godin Images, coming back to that. I must apologise, to a degree this isn't all about Python, but it is all about OpenStack and this OpenStack mini-conf, so please do shout out questions. So a Godin image encapsulates a known good set of software. When you start with an image that you haven't blessed yet, it's not golden, it's just a disk image. Once you're convinced it's good, then it becomes the Godin image. We exclude configuration and persistent state from the image. Now, the way we do this is, it's not kind of pure. We don't delete every single configuration file and then say, hey, there's no configuration there. What we do is that we don't generate the configuration files that we're going to use for our actual key services. Things like NTP, you'll just leave in the image, but things you're going to reconfigure or be able to tune or tweak, we generate at runtime. Today, the separate state partition thing is hypothetical, but we've got proof for concepts, we just haven't polished it. The LSB and, it's a well-known sys7 thing to be able to put these things on different partitions, so we're just going to be digging that up and polishing it in the OpenStack context. The interesting tweak is we want to make the base image itself, when it's mounted on a machine, read-only, so that we can be confident if we switch it out at any point in time with a new image, everything should be good, because nothing valuable has been written there. We want to make an error to try and write something valuable, something you want to keep, to the place that will be replaced when we redeploy the machine with a new image. The way I think about Godin Images is they're kind of like packages. Packages let you customize a machine. Godin Images let you customize a cluster. And they can be tested as an atom, they can be deployed as an atom, and there's no change between your test and deployment cycles. So it's exactly analogous. I mentioned the toolchain stuff before.
Sorry, just with the Godin image, just to be clear, so in that case, would you have, let's say you needed Redis installed on one of these Godin images, would you install that in the Godin image, or would that come in the configuration plan?
Sorry, I did a really silly thing. I started fiddling with my mouse rather than listening to your question.
Right. So any parts of your stack, like for example Redis that's a standalone,
Yep.
Would that go in the Godin image, or would that come later on?
I would put that in the Godin image.
Yeah, but not the configuration of Redis, that would come later on.
Yeah. So the way, so let's talk about the os refresh config cycle, because that will speak to your question. When you boot the machine, the first thing it does is it connects to the metadata server and pulls down enough configuration data from that, the EC2 compatible metadata server, pulls down configuration from that to be able to talk to heat. Once it talks to heat, it then gets your topology, the configuration data for the machine, and it runs os refresh config. Os refresh config runs a series of script directories. So it has a pre-configured directory and it runs everything in that directory, a configured directory, a post-configure, and a migrations. The steps I've got up here are talking about these are what we do using that framework. Using that framework, we quiesce the fragile services. Using that framework, we upgrade the disk image by copying it out a glance and overlaying it onto the current machine if we need to. So we don't need to reboot unless you've actually changed the kernel. And sometimes you need to reboot. So the way configuration gets written is for something like Redis, is that you would say, well, let's assume that Redis handles you editing the configuration files while it's running. Most services do. When you first boot the machine, Redis will fail to start up properly. You say, I don't care. Because the very first thing the machine does is goes back and says, phone timer says, give me my config. Writes the config down to disk and it runs through the pre-configure. There'll be nothing specific for Redis and pre-configure because Redis doesn't care if you change the config while it's running. It takes effect when you tell it to reload. The configure step probably doesn't have anything specific to Redis either because Redis just takes a template, a config file that's plain text. So you'll have a config file in OptStack, osapply config, templates, etc., redis.conf, something like that. And that's a moustached template. So you've got things that are always going to be true for your Redis will be fixed values, and things that are going to be coming out of the heap metadata will be JSON lookups. So just the dotted path through to the object you want. When os refresh config runs the configure step, one of the steps we have in there is the thing that says rewrite all the config files. So new config files blatted out. In the post configure step, you'll say, I always want Redis running, so check if it's running. If it's not running, start it. If it doesn't start properly, error. And at the end of the whole process, if an error occurred, or if it didn't, we tell heap where we got to. If a deployment fails on a node, you don't want to keep rolling out that new deployment to all the rest of your cluster. You want to stop and fix it, or even roll back. If it did work, you want to go on to the next one. Does that? Yeah. So the Puppet and Chef thing, we want to work with people that need Puppet or Chef and need complex system management capabilities. We don't want to cut anyone off from what we're trying to do. So the tools we've got are deliberately really, really narrow. Like they maybe do 10% of what Chef or Puppet or Salt does. And that's great. Use Chef or Puppet or Salt, or what's the other one that's... Ansible, yeah. Use it. Use it in collaboration with what we've got. The templates we're producing, the base capability we're producing should be completely compatible with someone overlaying Chef or Puppet on top of it. You could even use one of those tools to deliver the metadata to the machine. Because we've got small tools, plugging in a different front end for one of those tools is really easy. The way Heat works is that there's an API server, you talk to the API, and the API can give you metadata. When it boots the machine, it creates a temporary token for that one machine to be able to talk to the metadata server and ask for data, and also to feed data back and say, hey, this is a configuration value I'm exporting out to the cluster. So Heat, and I guess this is one of the things, Heat has no role within a machine. There are tools that work with Heat that you can run within a machine, but the Heat server itself is completely decoupled. There's a really clear abstraction layer. You can write alternative tools to talk to the Heat API, and you can also write alternative implementations of the Heat API. And Heat itself is a re-implementation of the Amazon CloudFormation API. But it's grown and matured and has got a different, and I think cleaner, kind of focus to it over time. Started by Red Hat, in fact. This is the bit where, so we've talked through all the plumbing. Now we're going to talk about some of the stuff that we do with it. So a deployment is really quite simple. Heat has the metadata that describes how many machines there are in the cluster, what disk image they're running, so the whole topology, right? Heat will drive the Nova API and say, please boot a machine with this image and this initial metadata connected to these networks and these block storage devices for me. And it does, and so it just iterates over your whole definition doing that until it's all up and running. Really easy. You can run Heat in DevStack on your local machine, so you still use Heat to do this testing locally. But rather than deploying to physical machines, you deploy it to VMs on your laptop. Dead easy. And this is one of the benefits of having the same API that I was talking about before. And yeah, for actual final pre-production testing, you probably want to always be deploying to bare metal. So bare metal for CI/CD and for production deployments. Now, I think this is still kind of slow, but that's mainly because the BIOSes on server class machines are really, really slow. And at least it's better now than it used to be. It used to be that big enterprise class hardware would take an hour to post. So yeah, we put together a proof of concept in a test rack at HP. We've got 40 odd machines, we're running Grizzly. It took us about a week to work through bugs which we hadn't fixed and use cases we hadn't quite got right in our code base. But once we actually had and we were doing the full thing, so we weren't cheating and just sort of manually installing it. At each point we were fixing little bits of automation or templates or so on, so that we're actually just manually walking through the tooling we have. So we brought up an UnderCloud. In fact, I may have to come back to some stuff. We brought up two clouds, a bare metal cloud and a virtual cloud. And the bare metal cloud is like one machine. It just has the control plane to be able to do the PXE and IPMI stuff. And then the virtualized cloud is the other 39 mumble, except a bunch of the hardware was misconfigured and we didn't have the right IPMI details. So we ended up with 20. But once we had that UnderCloud control plane and we got the OverCloud control plane in place, I could then drop and rebuild the whole thing in about 10 minutes. So I think that's pretty good. I think that it was really, really nice for me to be able to see that this is very competitive with the performance people get out of Chef or Puppet. And by competitive, I mean much faster. Here it is. I really should tweak these slides around. So the UnderCloud and OverCloud. The UnderCloud is your admin-owned cloud. It owns the hardware. It owns delivering anything. It can deliver Hadoop as well as OpenStack. Doesn't matter. It's your bare metal cloud. And for a number of reasons, we keep it completely separate from the OverCloud. And the OverCloud is the actual end-user cloud that's got KVM instances and that you put workloads on. The reason we keep it separate is twofold. One is, at least from a public cloud perspective, you really can't do bare metal end-user tenants today. There are so many ways people can gain permanent control of a machine if they ever run in ring 0. It is just not funny. It is a security nightmare. they can rewrite the firmware on an esoteric little device somewhere in the corner of the machine, and then on every boot, that code will run in ring 0 and game over. And that's without, potentially they can do that to the hard drive firmware on one of the hard drives. Like, when I say something in the corner that you won't notice, I really mean it can be way down in the corner. Separately, the hypervisor scheduler issue I was talking about before is still present. It's still not easily worked around. So even if we thought security-wise it's completely fine, it's actually really tricky to make it run properly reliably. You might be able to run separate Nova cells, one cell for bare metal, one cell for virtual, but I'm not sure that's enough of a gain over just running 2 clouds. If deploying a cloud is easy, just deploy 2 clouds. And since deploying a cloud is pretty easy, so this command line in the bottom right, yeah, you can't see that, can you? Yeah, the very bottom line there, that deploys a new cloud using heat. It's now in the middle of the screen. Create a cloud. I want an undercloud. Power user is just a parameter I'm passing in to say this is how you talk to Versh on my test environment. And it's one command. So you can get down to that easy. Who cares about the fact you've got 2 clouds? You've got a little bit of administrative overhead, but since the bare metal cloud is only used by your sysadmins, you don't have the same churn on that you might amongst an end user population. Wow, this is going to be a sprint to the end, I think. So the interesting thing for me about this arrangement is that you can run a pre-prod cloud as just another tenant on your undercloud. If you had one cloud and you tie them together, that's actually much harder to say, I will safely run an experimental test of my next deployed cloud in that environment, because it's actually going to be interoperating with the same control plane services for authentication or for scheduling. And if you manage to trigger a bug with your new version, particularly a cross-version interoperability bug, you could take down everything. Whereas if you say we've got completely separate clouds, one that owns the bare metal and one that's deployed on the bare metal, then you can just run 3 tenants of the undercloud, one production, one pre-prod, one CI/CD. Done. So I'd kind of describe that. This is the undercloud. At the moment, the way we deploy this is we actually have another cloud down the bottom here, the SeedCloud. And the SeedCloud lives as a VM on somebody's laptop. And you walk into the data center, you run the SeedCloud, you register a bare metal machine with it, you use that to deploy the undercloud, then you use the undercloud to deploy everything else. Okay? But the problem is that you then can't take that laptop away. Well, you can, things will keep running, but you need to walk it back in every time you want to change your undercloud, get a new version of software onto it, that sort of thing, which can be fairly rare because all it's doing is deploying to machines you've already got, right? It probably doesn't need to change capabilities that often. What we want to do is we want to make the bare metal cloud there, the undercloud, completely self-contained. And to make it self-contained, what we need to do is make it both high available and we need to make it do its own deployments to itself. So all of the services involved in doing deployment need to be able to be taken down mid-deployment and brought back up again and transfer the workload over. So they need to be stateless API web services, basically, with a stateful backend. And then the only bit that gets really hairy is moving your stateful backend, your MySQL cluster stuff around. Today, we do that by hand, in that we don't do full HA because we're not finished, but we've got scripts that go most of the way. And what we want to do in future, though, is we want to use Trove, the OpenStack DB API, which runs on top of Nova. So we want to have Trove running on Nova to provide the databases for the undercloud Nova API implementation. We want to make it, I think we can break the dependency loop at the install well enough because we've separated configuration and installation. That's fine, conceptually good. It's going to be fun. And this is why I'm in here, because this is just fun stuff, right? OverCloud I've talked about. Because the OverCloud is running as a tenant on the bare metal, the same image that provides the Nova control plane for the undercloud can provide the Nova control plane for the OverCloud. If you're running the undercloud as one machine, probably not, because you've got bare metal rather than KVM. But if you split out the undercloud because you've got tens of thousands of nodes, then you can reuse the images. I just mentioned this, the deployment. So the way we're going to get rid of the seed node is we'll deploy the seed node, we'll walk in. Rather than deploying a separate cloud with it, we'll just scale it out. Or we might deploy a separate cloud, but the separate cloud we deploy, rather than using the heat from the SeedCloud to deploy it, we'll migrate that heat into the UnderCloud and then scale out to 2 nodes. So it's a buy your bootstraps kind of operation. So I hope there are questions, because we've got 5 minutes to fill. There is something really fun about the acoustics here. Oh, these slides are... So I must admit, I've given this talk a few times because it's a very a thing lots of people are interested in. So the slides are all up on my Twitter stream. Yeah, so I'm at RBT Collins on Twitter, and if you go back far enough, you'll find a link that says, you know, triple O and triple O talk slides. I mean, you're welcome to copy them down, just saying.
What's the difference in function and use case between heat and something like Zookeeper?
So heat is domain specific. Zookeeper is general infrastructure. Zookeeper, so the Zookeeper is a distributed database, hierarchical with ACLs on it and events. Heat is, I am a template engine that takes a template description of a cloud, and I know about rolling deploys, for example. These features aren't all in Heat, but it's clear that if you said to Zookeeper, I want to talk about rolling deploys, they're going to go, eh?
Makes sense, thanks.
So I know there was a gentleman in the audience who was very interested in deploying Django on top of LXC on top of OpenStack. There must be a question from him.
Just a random comment. Your 6 minutes is way faster than anything I ever saw with Crowbar.
Told you. Tim and I talked about this back at LCA, and I didn't have timing data then. I was just like, this is how we're going to tackle the problem, and now we have, and yeah. That, by the way, that is about 95% post. We should be able to get it down to 3.5 minutes when we start using kexec rather than doing a full reboot to go between the deployment and the deployed instance.
I just wasn't too sure about how you deal with servers that have RAID controllers and lots of disks, or strange arrangements of disks, that sort of thing.
So yeah, this is the problem that basically, to describe this fully, I need to go through the whole OpenStack API and say, well, this bit of the API we use in this way, and so there's an API in OpenStack called Cinder, which talks about block storage. And when you think about RAID on a machine, the same things you might want to do for block storage, I want highly available block storage, or I want very fast but I can tolerate failures. Those are the same trade-offs you make when you reconfigure a RAID controller. So what we want to do is we want to have a stub driver in Cinder that will talk to Ironic. So you can say to Cinder, I want a volume and I want it in RAID 5 or RAID 6, and I want at least 20 spindles and I want at least 4 terabytes of data. And then when you say to Nova, please boot either with volume or from volume, with that volume ID, Ironic will say, hey, that volume, I haven't allocated it to a machine yet, so it will look at the pool of machines for a machine that can be reconfigured to that, and then tie them together in its database so that you always have to use that volume ID to land on that machine. And in its deploy RAM disk, before it actually copies the image on, it would run a vendor-specific tool for that RAID card to reconfigure it. And the way we'll orchestrate that is we'll pass the description into the RAM disk, and then you can have a RAM disk that interprets that description in any way you want. The current status of it is that this is all completely manual, so you can't do the stuff with Cinder. So the way you do it today is you just change your RAM disk to look at the machine and to reconfigure the RAID controller, which is nowhere near as graceful, but it, you know, it does the job. Or if you're buying some vendors like HP hardware just defaults to a fairly sensible RAID 5 over everything kind of setup, so you can often just ignore it with a lot of hardware. Some use cases, though, will depend very heavily on having it configured the way they need it configured.
Done a proper SVG.
This is from it. So some dude did this like 3 presentations ago, and it's been updated. Yeah, there's an SVG out there for it.
I mean, like the complete one that this is glossing over.
I don't think anyone's crazy enough. More seriously, I don't think it's useful. I mean, the point of this is to communicate the overall structure to people. The fact that it is more complex because the interactions between components is kind of implied. By the time you needed a diagram this busy to describe what's going on, you can be fairly sure that there's stuff being skipped.
So leading on from the gentleman in the front's question, with the UnderCloud especially, or ironic going straight onto bare metal, it seems it would be much easier on much more generic hardware across the board rather than like a bunch of
There it goes, it works.
servers that that are all different. Is that the case, or does it not really matter?
So there's 2 answers to that. Today it matters a great deal because Nova Bare Metal was the right one to throw away. That's Nova Bare Metal, right? Ironic understands that each individual node, so each individual thing you can address as a machine might actually be part of a chassis containing many machines, and each chassis might need a different way of talking to it to turn machines on or off, to configure things and so on. That's one dimension. And then another dimension is the actual hardware within the machine. They might be different architectures. Some might be ARM, i386, x86-64. They might need different RAID drivers and so on. So the way we handle those things today, Nova Bare Metal, you have one driver for the lot. You're screwed if you have any variation there. Deal. But what you can do is run multiple Nova computes configured for bare metal with a separate bare metal database, separate configuration file each, and this configuration file is then specific to that type of hardware. And when you register the hardware in Nova Bare Metal, you tell it which compute node is going to own that hardware. So you can deal with different architectures. You can deal with different control drivers, chassis drivers there. To deal with different architectures, when you describe the bare metal node to Nova, you say, this is of this architecture. That's fine. That's handled in bare metal and in Ironic. To deal with different RAID controllers and so on, basically use a good operating system like Linux, where you can throw every single driver under the sun into the one image. As long as it's for that architecture, every driver, done. Then you have one RAM disk, deployment RAM disk and kernel pair per architecture, so one for ARM, one for i3, right? And the tag on the machine that says it's ARM means only ARM. In addition to that tag, we also have a description of which RAM disk to use to provision that machine. So anything that matches that flavor, okay, that matches ARM, you're fine, and the flavor defines the deployment RAM disk. So there is some complexity there, but actually the complexity doesn't grow beyond having one bare metal machine at all. To do a bare metal machine, you need to create a deploy RAM disk, you need to put your tools in it.
Cool. Now, I know a couple of you still have questions for Robert, but we are over time for this presentation. I'm sure everyone wants to get to lunch before the Django people steal all of it. So I'd like to